Hi everyone, I am Pallavi. I'm a postdoc at LIDS MIT, and this is my work with Professor Illich on data-driven design and control of low-carbon microgrids for developing communities. We know that millions of people lack access to basic electricity, and a large majority of world population still relies on poor quality state electrification in developing countries. This work proposes interface problem between the on and off grid solution for the last mile electrification. We all have seen the grievous repercussions of the climate change across globe, and we know how urgent it is for all of us to switch to the renewable energy resources. The world leaders in energy are now saying that it is easier to develop a green energy infrastructure in developing countries rather than converting the already established carbon emitting energy nexus in developed countries. And this entire work points towards the direction of the SDG 7 of the United Nations, which says that we should provide reliable, universal access of energy to all in a sustainable way. If we are going for last mile electrification, it won't just happen using the centralized resources. What we need is a combination of both centralized and distributed. So this work mainly talks about a distributed generation based microgrid, where we are going to look at some of the advantages, challenges, and the design considerations of using a distributed generation. So advantages include improvement in power quality for loads, which is a big issue in developing countries. It also includes reduction in transmission and distribution losses because you can have control at several points in the grid now, so flatter feeder voltage profile is possible. And this additionally helps us incorporate renewable energy resources within the system like PV, wind, microhydro, etc. But it comes with its own challenges like limiting fault currents that we need to take care of. It requires a lot of fast switching because it now involves electronic converters which operate at high switching frequencies in the range of kilohertz. And the cost of the systems as of now are much higher. So when we talk about designing these distributed generated microgrids, we have to be sure that they compare well compared to the conventional power systems. And we have to make sure that the customization of these microgrids are based on both spatial and temporal constraints, thereby satisfying the needs of that local area, that community that these resources are serving. So while benchmarking these DG systems, we need to make sure that the costs are such that the fossil fuel based energy generation costs are matched, or we have some cost benefits. So the objective of this work is to design and control a green microgrid where the design considerations are as follows. We select the renewable energy resources depending on the local resource available in that area. If it is a tropical region, it has good sunlight, or if it has nice wind blowing, then you can use a wind turbine there. And another thing is about the size of the resource. So this can be evaluated using the historical weather data. Whether sun shines for how many hours in a day, etc., can help us. In what seasons also can help us decide the size of the renewable energy resource like photovoltaics, PV. The next thing is about the selection of the critical loads, what the community needs. Like, do they just need lighting, or do they also need some fans, some water pumping for irrigation, etc.? What are their critical loads that need to be determined? Next thing is about the storage, right? So if we need flexibility in the system to operate the system, even in the nights, if it's a solar system, etc., you need backup. And how much of it you need for critical loads. Yeah. And the power conditioning interface, like what power converters, AC, DC, 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 or DC, AC, what kind of power conditioning interface is needed in the system, that needs to be decided. And depending upon the community where the microgrid is being established, how many number of prosumers which are consuming and producing the power both are needed in the system. And the microgrid should have the flexibility to add or remove more resources as the time passes, right? Because the new technologies are coming up, some technologies are dating. So this flexibility is very important. And all the design considerations should meet the economic and performance criteria. When we come to the control, we have to make sure that the renewable energy generation, for example, solar energy needs to be scheduled in such a manner by seeing the historic weather data. So operation and scheduling needs to be done accordingly. We have to make sure that the source uh, is scheduled in such a manner that it is able to serve the loads, even if the local utility grid is present or absent, which is quite common in developing communities. They don't have 100% grid availability always. Then the battery lifetime, because battery is like the weakest link in the entire infrastructure, because they need a lot of operations and maintenance. Costs are involved. So we have to make sure they are not cycled unnecessarily. So battery lifetime management is another big issue that needs to be addressed. Um, and then there's further optimization in terms of load scheduling by observing the patterns of the loads over time and seasons and scheduling them in such a manner that the system is not overloaded at any point of time. Then the use of actual data from developing nations to understand the seasonal load patterns and load forecast. And all these control decisions need to maximize the efficiency, reduce carbon release, and be economically feasible. So the methodology that we are considering here actually incorporates the real field constraints. For example, if you look at this kind of a microgrid, which can have different resources, and let's say we choose solar out of this, solar and battery and diesel genset and some local loads and utility grid. So we are not considering the wind or hydropower or EVs or hydrogen storage right now in this particular example. Or you could, as the time passes, these things can be incorporated in the cost benefit analysis. So for the solar microgrid example with storage and grid availability, we have to see at what time we have to operate the grid tied PV systems so that the power production is maximized and the power quality is high. Another thing that needs to be considered is that when there is no grid utility grid available and there is no sun shining, the people would run a diesel genset to make sure that local loads are met. So this is an important consideration. And in the night, if you don't have such a provision and you don't want to burn the diesel in the diesel genset, then the battery storage is definitely needed. Right. And we also need to take care of the fact that sun shines not throughout the day, but let's say 12 hours in a tropical country, but that too not, it's a diffused resource. It doesn't shine at the constant power all the time. So let's say a peak capacity factor of 0.45 would means that for half of the time, you can assume a flat peak power production from the solar resource. So on an average, the peak power is for around 5 hours per day for a 0.45 peak capacity factor if the sun is shining for 12 hours in a day. So all these practical constraints need to be incorporated into the methodology. So like I said, in the case study that we are considering here, we have a solar microgrid for a developing community, and we determine the minimum cost of energy without compromising the operating performance. And this we do for local loads, where we talk about the critical loads varying from 0 to the maximum that this particular 3 kilowatt microgrid can serve. And we assume that to prevent battery aging and to have a good lifetime for the battery, we charge it by the grid power. And we use the sun to serve the local loads and to supply the excess power to the grid to prevent excess cycling of the battery. In the night time, as we can see, the battery or the grid supplies the load and the grid also charges the battery. Now, if there is no sun and no grid and the battery is discharged, then the diesel genset might be used. And the cost of energy for that has been determined for an Indian scenario, which is in Indian national rupees, 17 rupees per kilowatt hour. And the grid cost of energy in India is typically 6 rupees per kilowatt hour. So now looking at the power converter, what kind of a power converter should we choose? So depending on the efficiency of the converter and the cost of the converter, we can decide what would be the best case for us. So typically we would want a power converter to have zero power loss, zero volume, zero weight, zero cost, right? But actually it has actual constraints like physical values. It is not infinitely efficient, right? So all the above trade-offs are considered into the analysis so that we come up with the best configuration. For this case, it comes out to be this middle one. For the critical loads, depending on the community needs, so as the household income typically increases, people add in more loads in their system and more critical loads in their system. For example, you see typically in a rural household, people would put some lights, some fans, refrigeration if they are rich enough to have a refrigerator in their systems, some cooking loads or some part plugs, right? And non-critical would include water pumping, they can do it when the grid is there, right? Air conditioning, water heaters, entertainment like television, battery charging, etc. So we know that as the size of the household increases, or as the income of the household increases, the loads increase, and the critical loads also increase in time. And also with upcoming technologies and the needs of the community as they grow, as the community advances, then it is possible to have more loads. Also, there's a seasonal variation in the loads depending on, uh, let's say, in there's a rice harvesting season, that's when they need more water. So agricultural loads also kind of add to what is critical and what is not. So if we think about optimizing overall the system, we would say let's reduce the cost of the battery management system, because batteries are the weakest link in this entire microgrid, because solar panels are quite robust, utility grid is quite robust. It's the batteries which need a lot of maintenance. So how do we optimize the battery cost or the cost of energy of the system? This is by scheduling household loads and the sources like sun and the grid, subject to the availability of the grid, the solar forecast, resource forecast, and the critical loads or the user comfort. So this is roughly the optimization problem that we can tackle. And if we look at the load scheduling, it can be done day ahead manner. For example, when I would want to pump my water, it can be done in a weekly manner, like when I want to do my laundry, or it could be done on a monthly basis depending on the weather patterns, like when do we need heating or cooling loads. So cost of energy is defined as the annual cost incurred per unit electrical energy produced. So this includes capital cost, operations and maintenance cost, fuel cost, and if there are any benefits like not using diesel, genset, etc., that gets subtracted. And total energy is basically how much energy your renewable energy resource is producing. That gives the cost of energy. So when we see that there's a grid outage, we did this analysis some time back, and we saw that as the grid tide inverters see more outage, the cost of energy becomes really high. This is for an Indian scenario, so in rupees. And the price of batteries actually getting balanced as more and more hours of grid outage are there in the system. If there is a nighttime outage when the solar PV systems cannot operate, grid-tied system, that's when the batteries operate, and you can see the saturation happening in the battery limit. So if you want more critical loads in your system, the saturation will happen faster, and you would need to invest more in your batteries. Similar analysis can be adopted for wind power generation. You have wind turbines, you have the gearbox, the generator, the power converters, which is connected to the grid. Now the question is, the different equipments, different blocks here have different efficiencies and different costs associated with them. So this amounts to 100% of the system cost. And like we did the cost of energy analysis, same thing can be applied here for high efficiency and low cost optimization. And for example, if the power converter here has a higher efficiency, then the overall losses in the system reduce, but it amounts to just 10% of the system cost. So you can even go for a higher efficiency system because the cost would not be added so much. Similarly, if the smart power converter has variable speed drive, you would be able to capture more energy, and thereby you can reduce the size of this blade, which is a huge chunk of the cost of the entire system. So different levels of optimization are possible. In conclusion, we can say that this case study can further be extended to redefine performance objective for developed countries, considering load sensitivity to power quality. And the present analysis considered not just the varying critical load, but it also redefines how we can predict the slow varying and the fast varying load component from the historic data. It uses the generation forecast for renewable energy resources like solar photovoltaics. It can day ahead schedule the battery charging and discharging depending on the grid availability. And whatever are the deviations in the load, it can further help in enhancing the frequency stability in distributed generation while allowing less regulation on inverter side. Further enhancement of this study to include both centralized and distributed storage, considering smart coordinated control, can lead to quantifiable optimized performance. And in a nutshell, the idea of this tertiary level optimization is to have Depending on the load profiles of the critical and non-critical loads, state of the charge of the battery, solar power generation, grid availability, we should be able to find a cost-effective solution which is efficient, meets the performance criteria, and emits low carbon in the atmosphere. So thank you so much for listening to us. These are some of our references. And if you have any questions, please feel free to share it with me or my senior author. Thank you.